Most of us turn on a tap without thinking. Clear water appears almost instantly, but that simple moment hides a vast system. Pipes, pumps, reservoirs, treatment plants. Every drop of water travels a long and careful path, often across mountains, through tunnels deep underground, and through machines designed to clean it. Tonight, we will quietly follow that journey. From rivers and rainfall to the glass of water beside you. This is the hidden infrastructure of everyday life, and how water reaches your home. When you turn a tap in your kitchen or bathroom, something very quiet happens. Water begins to move through a system you cannot see. It travels through pipes hidden in walls, pipes hidden under streets, pipes that run across entire cities. Most people never notice this system. It works quietly in the background of daily life. A glass fills. A shower runs. A kettle begins to heat. The water simply arrives. But behind that simple moment is one of the largest engineered systems humans maintain. Entire regions are designed to move water safely and reliably. Engineers plan it. Cities maintain it. Gravity and pressure quietly guide it forward. All of this exists so that a small metal handle can release clean water within seconds. This system is called the municipal water supply. Nearly every modern city depends on it. Millions of people share the same network of pipes and reservoirs. The network spreads outward like the branches of a tree. Large pipes carry water across long distances. Smaller pipes divide into neighborhoods. Even smaller pipes enter individual buildings. At the very end of this network sits a simple tap, a small point where a massive system becomes invisible again. For most of human history, this convenience did not exist. People carried water by hand, from wells, from rivers, from public fountains. The process required time and effort every day. Water was heavy. It spoiled easily, and it was often unsafe to drink. Cities grew slowly because water could not easily travel long distances. Over centuries, engineers began solving this problem. Ancient civilizations built early water systems. Stone channels carried water downhill. Clay pipes moved water through towns. The Romans constructed long aqueducts to guide water toward their cities. Gravity did most of the work. Water flowed slowly but continuously. These early systems were impressive for their time, but they were limited in scale. Modern water infrastructure grew much larger during the 19th and 20th centuries. Cities expanded rapidly during industrialization. Populations grew into the millions. Supplying clean water became a public necessity. It was not only about convenience. It was about health. Diseases such as cholera spread through contaminated water. Engineers and scientists began designing systems to filter and disinfect water. Gradually, the large municipal systems we know today took shape. These systems operate quietly beneath our feet, under sidewalks, beneath roads, below parks and buildings. Thousands of kilometers of pipe run under a large city. Some pipes are wider than a car. Others are only a few centimeters across. Together, they form a layered network. The largest pipes carry water across regions. Medium pipes distribute it through districts. Small service pipes finally connect individual homes. Most of this infrastructure remains hidden. Once installed, pipes may remain underground for decades. Some pipes continue working for more than a century. Crews inspect them occasionally, but most of the time they simply do their job quietly. This hidden nature makes the system easy to forget. We rarely think about water pressure, or pumping stations, or treatment plants. Yet every time water flows from a tap, those systems are working together. The journey of drinking water begins far away from the home, often in mountains, or lakes, or underground aquifers. Rain falls, snow melts, rivers gather the flow. From these natural sources, cities collect the water they need. But water from nature is rarely ready to drink. It may contain sediment, microorganisms, organic material. Even clear mountain water can contain microscopic life. Because of this, modern systems include careful treatment steps: cleaning the water, filtering it, disinfecting it. Only after these steps can water safely enter the distribution system. At that point, the challenge becomes transportation. Water must travel long distances, sometimes across entire regions. Engineers rely on two main forces to move it: gravity and pressure created by pumps. Gravity works whenever water begins at a higher elevation. Water naturally flows downward through pipes and channels. Many reservoirs are built on hills or mountains for this reason. Height creates natural pressure. Pumping stations assist when gravity alone is not enough. Large electric pumps push water upward or forward through the system. Together, gravity and pumps keep the network moving. Another important feature of the system is storage. Cities cannot rely on a constant supply from nature every hour of the day. Demand changes throughout the day. Morning showers create one peak. Evening cooking creates another. To balance these changes, water is stored in reservoirs and tanks. Some reservoirs sit on hills above cities. Others are tall water towers rising above neighborhoods. These structures store water when demand is low and release it when demand rises. They also help maintain steady pressure throughout the network. Pressure is essential for water to reach upper floors of buildings. Without pressure, water would only flow at ground level. Engineers carefully design pressure zones across a city. Each zone maintains a safe and reliable range of pressure. Too little pressure would slow the flow. Too much pressure could damage pipes. Balancing this system requires careful planning. Even the materials of the pipes matter. Older systems used cast iron pipes. Many of those still exist today. Modern pipes may use ductile iron, steel, or durable plastics such as PVC. Each material must resist corrosion. It must handle pressure changes, and it must last many decades underground. Despite the complexity, the goal of the system remains simple. Provide safe water, deliver it reliably, and make it available at any moment of the day. The system must operate in winter and summer, during storms, during heat waves. Most of the time, it does this quietly and without interruption. When it works well, people rarely think about it. That quiet reliability is part of its design. The infrastructure disappears into everyday life, hidden behind walls and underground tunnels. Yet every drop of water you drink has traveled through this vast system. A journey shaped by geography, engineering, and careful public planning. To understand this system clearly, it helps to begin where the journey truly starts. Not in the pipes beneath the city, but in the natural sources that provide the water itself. And that journey begins with the places where cities collect water from rivers, lakes, reservoirs, and underground aquifers. Every city must begin its water journey somewhere. Before pipes and pumps exist, there must be a source, a place where water naturally gathers. These sources are part of the Earth's natural water cycle. Rain falls from clouds. Snow collects on mountains. Rivers carry water downhill. Some water sinks into the ground. Cities draw from these natural movements of water. The first common source is surface water. Surface water includes rivers, lakes, and reservoirs. These bodies of water are visible on the landscape. They collect rainfall and melting snow over large areas. Engineers often call these areas watersheds. A watershed is the land region that drains water toward a river or lake. Rain falling anywhere in that region eventually flows toward the same basin. Mountains, forests, and valleys guide this flow. Rivers are one of the oldest water sources for cities. They carry large volumes of water over long distances. Many cities were originally built near rivers for this reason. Rivers can provide a steady supply of fresh water, but they also change with the seasons. Heavy rain increases their flow. Dry seasons may reduce it. Because of this variability, cities often combine river water with other sources. Lakes are another major surface source. Large lakes store enormous volumes of water. They act as natural reservoirs. Their size helps stabilize supply during dry periods. Cities located near large lakes often depend heavily on them. Water can be drawn from deep intake points far from the shore. These deeper areas often contain cleaner and cooler water. In many regions, however, natural lakes are not large enough to meet demand. For this reason, engineers construct artificial reservoirs. A reservoir is a large body of water created by building a dam across a valley or river. The dam slows the flow of the river. Water gradually fills the valley behind it. Over time, this stored water becomes a stable supply for nearby cities. Reservoirs offer several advantages. They store water during wet seasons. They release water slowly during dry seasons. This helps maintain a consistent supply throughout the year. Reservoirs also allow sediments to settle naturally over time. As water rests in the reservoir, heavier particles sink to the bottom. Reservoirs are often located far from the cities they serve, sometimes dozens of kilometers away, sometimes even farther. Engineers choose locations carefully. They look for valleys where dams can be safely built. They consider the surrounding watershed size. A large watershed collects more rainfall. This increases the long-term reliability of the reservoir. Many reservoirs are also protected areas. Activities near the water are often restricted. This helps prevent pollution. Fewer pollutants entering the reservoir means easier treatment later. Protecting the watershed is often the first step in protecting drinking water quality. Not all cities rely on surface water. Many depend on groundwater instead. Groundwater exists beneath the surface of the earth. It fills small spaces between rocks and soil particles. Over time, rainwater slowly filters downward through layers of soil. Eventually, it collects in underground formations called aquifers. An aquifer is a layer of rock or sediment that holds and transmits water. Some aquifers are shallow. Others lie hundreds of meters below the ground. The water inside them may have traveled slowly underground for years, sometimes even for centuries. Because of this long filtration through soil and rock, groundwater is often naturally clean. Cities access groundwater by drilling wells. A well is a vertical shaft that reaches down into the aquifer. Pumps draw the water upward to the surface. From there, it can enter treatment facilities or distribution systems. Groundwater offers several benefits. It is naturally filtered by soil layers. It is less affected by short-term weather changes. And it is often protected from surface contamination. However, groundwater supplies can be limited, is less than Hashon. Zero hash is greater than aquifers. Recharge slowly. They depend on rainfall gradually soaking into the ground. If water is pumped out faster than it refills, the aquifer level may decline. Because of this, cities carefully monitor groundwater levels. Wells are sometimes spread across large areas. This reduces pressure on a single aquifer location. Water managers track how quickly the aquifer recovers after rainfall seasons. Some regions combine both groundwater and surface water sources. This approach increases reliability. During wet seasons, surface reservoirs may supply more water. During droughts, groundwater may support the system. Using multiple sources helps balance risk. Geography strongly influences which sources a city uses. Mountain cities often rely on snowmelt stored in reservoirs. Coastal cities may draw from rivers flowing inland. Dry regions may depend heavily on underground aquifers. Each location adapts its water system to the landscape around it. Climate also plays an important role. Regions with steady rainfall may have many small reservoirs. Regions with long dry seasons require larger storage systems. Engineers design water systems with decades of weather patterns in mind. Another factor is population size. Small towns may rely on a few wells. Large metropolitan areas require vast water supplies. Some major cities import water from distant regions. Long aqueducts and pipelines carry water across mountains or deserts. These systems can stretch for hundreds of kilometers. Even when water is abundant, cities must still protect the quality of their sources. Pollution can enter rivers from farms, factories, or urban runoff. Chemicals and sediments may flow downstream. Groundwater can also become contaminated if harmful substances seep into the soil. To reduce these risks, many countries establish protected watershed zones. Land use is controlled in these areas. Industrial activities may be restricted. Waste disposal may be carefully regulated. The goal is simple. Keep the source water as clean as possible before treatment begins. Even with protection, natural water still contains many substances. Tiny particles of soil, organic material from plants, bacteria, and microscopic organisms. These are normal parts of natural ecosystems. But they must be removed before the water becomes safe for drinking. For this reason, raw water from rivers, lakes, reservoirs, or wells rarely goes directly into homes. It first travels to specialized facilities designed to clean it. These facilities are known as water treatment plants. Inside these plants, water moves through several careful steps. Large debris is removed. Fine particles are separated. Microorganisms are neutralized. Each step prepares the water for safe distribution through the city's pipes. Before any of that treatment can begin, however, the water must first be collected and guided away from its natural source in a controlled way. And that process begins with the structures that quietly capture water from rivers, lakes, reservoirs, and aquifers. Water exists in rivers, lakes, reservoirs, and underground aquifers. But cities cannot simply let this water flow directly into their pipes. It must first be captured carefully, controlled, and guided toward treatment facilities. This process is called water intake. A water intake is the physical structure where a city begins collecting raw water from nature. These structures are designed to do something simple: allow water to enter the system. while keeping unwanted materials out. Leaves, branches, sediment, fish and other aquatic life. All of these must remain outside the intake. The design of an intake depends on the type of water source. Rivers require one type of structure. Lakes require another. Reservoirs and aquifers require different approaches as well. But the principle remains the same. Collect water safely and steadily. One of the simplest intake systems is used for rivers. A structure is built along the riverbank, sometimes slightly below the surface. Openings allow river water to enter a channel or pipe, but these openings are protected by metal screens. The screens block large debris, sticks, leaves, floating objects carried by the current. The spacing of the bars is carefully chosen, wide enough to allow water through, narrow enough to block larger materials. River intakes must also handle changing water levels. During heavy rain, rivers may rise quickly. During dry seasons, water levels may drop. Engineers design adjustable intake points to manage these changes. Sometimes multiple openings are placed at different heights. Operators can choose the most stable intake level depending on river conditions. Lakes and large reservoirs often use a different structure called an intake tower. These towers stand in the water, sometimes hundreds of meters from the shore. They extend above the surface like small concrete buildings. But much of the structure continues below the waterline. Intake towers contain several openings at different depths. Each opening can draw water from a specific layer of the lake or reservoir. This allows operators to choose the cleanest water available. Water conditions change with depth. Surface water may contain more algae or floating debris. Deeper water may contain less organic material. Selecting the right depth improves water quality before treatment even begins. Inside the intake tower, water flows into a vertical shaft. From there, it travels through large pipes leading toward land. These pipes are often called raw water pipelines. They carry untreated water toward the treatment plant. Intake towers also include protective screens, similar to river intakes. These screens prevent fish and large debris from entering the system. In some locations, slow-moving intake flows help fish swim away safely. Protecting aquatic life is an important design consideration. Reservoir intake structures often work quietly for decades. They are built from reinforced concrete and steel, materials chosen for long-term durability in water environments. Regular maintenance crews inspect them periodically, removing debris, checking structural integrity. Groundwater sources require a different type of intake entirely. Instead of collecting water from open surfaces, cities drill wells into aquifers. A well begins as a narrow hole drilled deep into the ground, sometimes tens of meters deep, sometimes hundreds. The depth depends on the location of the aquifer. Once the hole reaches the aquifer layer, the well is lined with a strong casing. This casing is usually made of steel or durable plastic. It prevents the surrounding soil from collapsing into the well. The lower portion of the casing includes small openings called well screens. These screens allow groundwater to flow into the well, while blocking sand and sediment from entering. A pump is installed inside the well. This pump lifts groundwater upward toward the surface. Electric motors drive the pumping system. Sensors monitor flow rate and pressure. The pumped water then enters pipes leading toward treatment facilities. Wells are often distributed across large areas. Instead of relying on a single large well, cities may use dozens or even hundreds of smaller wells. This spreads the demand across the aquifer, reducing the risk of overpumping in one location. Some intake systems rely partly on gravity. If the water source lies at a higher elevation than the treatment plant, water can flow downhill naturally through pipelines. Gravity systems require less energy. They operate quietly and efficiently. Other intake systems rely heavily on pumps, especially when the water source lies at the same elevation as the city, or when water must travel long distances. Pumping stations help maintain a steady flow toward treatment plants. At many intake sites, the first stage of basic cleaning begins immediately. This process is called screening. Large metal grates capture floating debris, leaves carried by rivers, branches from nearby forests, plastic or other floating materials. Operators remove this debris regularly, keeping the intake clear and functional. Some systems include additional coarse filters. Rotating drum screens may slowly turn in the water flow. These screens trap particles while allowing water to pass through. Automated cleaning systems remove accumulated debris. This helps maintain continuous operation. Intake locations are chosen carefully. Engineers study water currents, sediment movement, seasonal algae growth. The goal is to find the most stable and clean portion of the water body. A well-positioned intake reduces the workload of the treatment plant later. Environmental monitoring also takes place at many intake sites. Sensors measure water temperature, turbidity, which indicates the amount of suspended particles. They may also monitor chemical conditions such as pH levels. This data helps operators adjust treatment processes later in the system. Another important feature is reliability. Cities cannot allow their water intake to stop unexpectedly. Backup pumps are often installed. Redundant pipelines may be constructed. If one component requires maintenance, another can continue operating. Safety systems also protect against contamination events. If sensors detect unusual water conditions, operators may temporarily shut down an intake or switch to a secondary source. These precautions help maintain safe drinking water for the city. Once the raw water passes through the intake structures, its journey continues underground. Large pipelines begin carrying it away from the natural source. The water is still untreated. It still contains sediment, microorganisms, and organic matter from the environment. But it is now moving under controlled conditions. These pipelines are often called raw water mains. They transport water toward specialized facilities where cleaning begins. Facilities designed to remove particles, neutralize microorganisms, and prepare water for safe distribution. And so the captured water continues its quiet journey, leaving rivers, lakes, reservoirs, and aquifers behind, moving slowly through large pipelines toward the place where the first true stage of purification begins. Once water enters the intake structures, its journey continues through large pipelines. These pipelines carry what engineers call raw water. Raw water means the water has not yet been treated for drinking. It still contains natural particles and microorganisms, but it is now moving within a controlled system. The distance between a water source and a treatment plant can vary greatly. Some cities build treatment plants very close to their reservoirs or rivers. In these cases, water may travel only a few kilometers. Other cities collect water from far away, sometimes from mountains or distant valleys. In those cases, water may travel tens or even hundreds of kilometers before reaching the treatment facility. These long-distance pathways are often called aqueduct systems. An aqueduct is any structure designed to transport water across a landscape. Aqueducts may be open channels, large tunnels, or enclosed pipelines. Many modern aqueducts operate entirely underground. Underground pipelines protect water from contamination. They also reduce evaporation from sunlight and wind. Inside these pipelines, water moves steadily toward the treatment plant. The pipes themselves are large. Some are wide enough for a person to walk through during maintenance. Others are several meters in diameter. Their size allows them to carry enormous volumes of water every day. Engineers carefully choose the materials used for these pipelines. Many raw water mains are made from steel or reinforced concrete. Some use ductile iron. Others use specialized concrete-lined tunnels. The materials must resist corrosion. They must withstand water pressure. And they must remain reliable for many decades underground. The movement of water through these pipelines depends on two main forces: gravity and mechanical pumping. When possible, engineers prefer to use gravity. Gravity systems require less energy. They also involve fewer moving parts. This makes them simpler and more reliable over long periods. Gravity flow works best when the water source is located at a higher elevation than the treatment plant. For example, a reservoir built in the mountains may sit hundreds of meters above a city. Water naturally flows downhill through the aqueduct. No pumps are needed to keep it moving. The slope of the pipeline is carefully designed. If the slope is too steep, water may move too quickly. This can cause turbulence or damage. If the slope is too gentle, the flow may slow down too much. Engineers calculate the ideal gradient for steady movement. Some aqueducts include tunnels that pass through mountains. These tunnels shorten the distance between water sources and treatment plants. They also allow pipelines to maintain a smooth downhill path. Tunnel construction can take many years, but once completed, the water can travel through them continuously. In flatter landscapes, gravity alone may not be enough. In those situations, pumping stations are added along the pipeline. A pumping station contains large mechanical pumps powered by electric motors. These pumps push water forward through the pipeline. Sometimes they also lift water upward to higher elevations. Pumping stations are spaced at intervals along the route. Each station adds energy to the water flow, helping it continue its journey toward the treatment plant. Engineers design these stations with backup systems. If one pump stops working, another can take over. Inside the pumping station, large pipes connect directly to the pumps. The pumps rotate powerful impellers. These spinning blades push water forward through the pipeline. Control systems monitor pressure and flow rate. Operators adjust the pumps if conditions change. Along the pipeline, additional structures help maintain safe operation. One example is a valve station. Valves allow sections of the pipeline to be closed if maintenance is required. This prevents the entire system from shutting down during repairs. Another important structure is the air release valve. Air can sometimes become trapped inside large pipelines. Trapped air can reduce flow efficiency or create pressure fluctuations. Air release valves allow this air to escape safely. Engineers also include pressure relief systems. If pressure rises too high inside the pipeline, relief valves release small amounts of water. This protects the pipeline from damage. Monitoring equipment is often installed along the aqueduct. Sensors measure flow speed, pressure levels, and water temperature. This information is sent to control centers where operators watch the system in real time. Even though these pipelines carry untreated water, cleanliness is still important. The pipes are sealed to prevent outside contamination. Maintenance teams inspect them periodically. Over time, sediments may accumulate along the bottom of the pipeline. Special flushing procedures remove these deposits when necessary. The speed of water flow inside these pipelines is carefully controlled. Engineers aim for steady, moderate movement. Water moving too slowly may allow sediments to settle. Water moving too quickly may cause erosion inside the pipe. Balanced flow protects the system and ensures efficient transport. Some long aqueduct systems include intermediate storage reservoirs. These reservoirs temporarily hold water along the route. They provide a buffer between the source and the treatment plant. If water demand changes suddenly, the reservoir helps stabilize the flow. These intermediate reservoirs also allow sediments to settle naturally. Heavier particles sink slowly to the bottom while the water rests. This simple process reduces the load on the treatment plant later. The journey through aqueducts and pipelines may take several hours. In very large systems, it may take an entire day. The water moves slowly but continuously, quietly traveling beneath fields, roads, and forests. Eventually, the pipelines approach the treatment facility. Here, the water leaves the long transport system and enters a carefully designed series of cleaning processes. At this stage, the goal changes. The challenge is no longer transportation. It is purification. Raw water arriving at the treatment plant still contains visible particles. Sand and silt from rivers, organic debris from plants, microscopic organisms living naturally in water. The first task is to remove the largest of these materials. This begins with the quiet process of separating heavier particles from the flowing water. A process that relies not on machines alone, but on the simple and steady force of gravity. Raw water eventually arrives at the treatment plant. It has traveled through rivers, reservoirs, intake structures, and long pipelines. It now enters a place designed for careful cleaning. Treatment plants are large and quiet facilities. Water moves through them slowly and continuously. Each stage removes something different from the water. The first stage focuses on the largest unwanted materials. Leaves, small sticks, bits of plant matter, sand and gravel carried by rivers. These materials are not unusual. Natural water sources always contain them. But they must be removed before finer purification can begin. The process begins with screening. Large metal screens sit at the entrance of the treatment plant. Water flows through these screens as it enters the facility. The openings in the screen allow water to pass through, but larger debris becomes trapped. Operators remove the trapped material regularly, sometimes by hand, sometimes using mechanical rakes. This simple step protects the rest of the treatment equipment. After screening, the water continues into large open basins. These basins are designed to slow the water down. When water slows, gravity begins to do quiet work. Heavier particles start to sink toward the bottom. This process is called sedimentation. Sedimentation relies on a simple physical principle. Solid particles in water are often heavier than the water itself. When the water becomes calm, those particles slowly fall downward. The heavier the particle, the faster it sinks. Treatment plants build large settling tanks to allow this process to happen. These tanks are wide and shallow. Water enters slowly from one side. It moves gently across the tank and exits from the other side. During this quiet movement, sand and silt settle onto the bottom. The settled material forms a layer called sludge. This sludge collects slowly over time. Mechanical scrapers move along the bottom of the tank. They gather the sludge and push it toward collection points. From there, it can be removed for disposal or further treatment. Above the settling particles, the water gradually becomes clearer. The heaviest materials are now gone, but many smaller particles still remain suspended. These particles are too light to settle easily on their own. Some treatment plants include an additional step called grit removal. Grit chambers allow sand and very small stones to settle quickly. The chambers slow the water just enough for dense particles to fall out. Removing grit protects pumps and filters later in the system. Even after grit removal and sedimentation, the water is still cloudy. Many particles remain suspended in the water column. These particles are often extremely small, sometimes microscopic. They include fine clay, organic fragments, and tiny microorganisms. At this stage, gravity alone is not enough to remove them efficiently. The particles are simply too light. They float slowly within the moving water. To remove them, treatment plants must prepare the water for the next stage of purification. But before that stage begins, operators carefully control how quickly water flows through the settling basins. Flow speed is important. If water moves too fast, particles will not have time to settle. If it moves too slowly, the plant cannot process enough water for the city. Engineers calculate the correct balance. Many treatment plants operate continuously. Water enters day and night. Sediment slowly settles. Sludge is removed in steady cycles. The process is quiet and repetitive. It rarely stops. The design of sedimentation tanks often includes special features to guide water smoothly. Baffles are placed near the entrance. These barriers spread the incoming water evenly across the tank. Even flow prevents turbulence. Calm water encourages particles to sink. At the far end of the tank, collection channels gather the clarified water. This water is now much cleaner than when it arrived, but it is not yet safe to drink. It still contains many tiny particles and microorganisms. Treatment plants measure water clarity at several points in the process. Instruments monitor turbidity. Turbidity is a measure of how cloudy the water appears. High turbidity means many particles are still suspended. Lower turbidity indicates clearer water. Sedimentation greatly reduces turbidity. But it cannot remove everything. Particles that are extremely small may remain suspended for long periods. Some may even carry bacteria or viruses attached to their surfaces. Because of this, treatment plants prepare the water for a more advanced process. A process that helps small particles join together into larger ones. Once they become larger, gravity can remove them more easily. This step requires the careful use of chemistry and controlled mixing. Before that happens, the water leaving the settling tanks already shows clear improvement. Most of the visible sand and heavy debris is gone. The water moves more smoothly through the plant. The system has quietly completed its first major cleaning stage. The remaining challenge lies with the smallest particles. Particles so small that they drift easily in moving water. Removing them requires a method that encourages them to gather together. And that careful process begins with the science of coagulation and flocculation. After the first settling process, the water is clearer than before. Heavy sand and large particles have already sunk to the bottom of the sedimentation tanks. But many tiny particles are still present. These particles are extremely small, often invisible to the human eye. They may include clay, organic fragments, and microorganisms. Because they are so small, they remain suspended in the moving water. Gravity alone cannot remove them easily. The particles are simply too light. Some even carry electrical charges on their surfaces. There is less than Hashone. 0 hash is greater than. These charges cause the particles to repel each other. As a result, they remain evenly dispersed throughout the water. To remove them, treatment plants use a process called coagulation. Coagulation introduces special chemicals into the water. These chemicals help neutralize the electrical charges on the particles. Once the charges are neutralized, the particles can begin to come together. One of the most commonly used coagulants is aluminum sulfate. It is sometimes called alum. Other coagulants may include iron salts or similar compounds. The exact chemical depends on the water source and treatment design. The coagulant is added in a controlled amount. Too little will not work effectively. Too much may create unnecessary chemical residue. Engineers monitor the dosage carefully. Sensors measure water conditions continuously. Once the coagulant enters the water, rapid mixing begins. Mechanical mixers stir the water quickly for a short period. This spreads the chemical evenly throughout the water. During this mixing stage, the coagulant particles begin interacting with the suspended materials. The chemical reaction reduces the electrical repulsion between particles. As a result, tiny particles begin to stick together. At first, the clusters are extremely small, but they begin forming larger structures gradually. This leads to the next step, called flocculation. Flocculation allows the small particle clusters to grow into larger groups called flocks. The word flock simply refers to these visible clumps of particles. They may appear like small floating clouds in the water. Flocculation requires gentle mixing rather than rapid stirring. Large paddles or slow-moving mixers rotate inside flocculation tanks. The movement is calm and steady. Too much turbulence would break the forming flocks apart. Over time, the flocks grow larger. Tiny clay particles join with organic fragments. Microorganisms may become trapped within the growing clusters. the clusters continue to increase in size. As the flocks grow heavier, gravity begins to affect them more strongly. Eventually, they become heavy enough to settle. This allows them to be removed in another sedimentation stage. The design of the flocculation tanks helps this process occur gradually. Water moves through several chambers in sequence. Each chamber mixes the water a little more gently than the previous one. This encourages the flocks to grow without breaking apart. The entire coagulation and flocculation process may take 30 minutes or longer. During this time, the water is constantly moving through the system. Fresh, raw water continues entering the treatment plant. The process operates continuously. Operators monitor the formation of flocks carefully. They observe water samples under controlled lighting. Healthy flocks appear as soft clusters drifting slowly in the water. If the clusters are too small, chemical dosage or mixing speed may be adjusted. The chemistry of coagulation depends strongly on water conditions. Temperature plays a role. Cold water slows chemical reactions. The natural acidity of the water also matters. This property is measured as pH. Engineers may adjust the pH slightly to improve coagulation efficiency. Natural organic matter can also influence the process. Water flowing through forests may carry plant-based compounds. Rivers flowing through farmland may contain different materials. Treatment plants adjust their chemical processes depending on the source water. Despite these variations, the basic principle remains consistent. Tiny particles must be encouraged to combine into larger groups. Larger groups can then be removed by settling or filtration. Coagulation and flocculation prepare the water for that removal. As the water leaves the flocculation tanks, the flocks are now clearly visible. They drift slowly in the water, heavier than the surrounding liquid, ready to settle out under calm conditions. The water now moves into another set of basins designed for that purpose. These basins resemble the earlier settling tanks, but this time they remove the newly formed flocks. Once again, gravity performs quiet and steady work. Over time, the flocks sink to the bottom of the basins. They form another layer of sludge that can be collected and removed. Above this layer, the water becomes significantly clearer. Many of the suspended particles have now been eliminated. Even so, the water is not yet fully purified. Extremely fine particles may still remain. Some microorganisms may still be present. The next stage of treatment focuses on removing these remaining materials through a physical filtering process. And that process begins as the clarified water flows slowly toward large filtration beds designed to capture the smallest particles that remain. After coagulation, flocculation, and settling, the water has become much clearer. Many suspended particles have already been removed. Large debris is gone. Sand and heavy sediment have settled out. The flocks formed during chemical treatment have also been separated. but the water is not yet perfectly clean. Some extremely fine particles remain. Some microorganisms may still be present. Very small fragments of organic material may still drift in the water. To remove these remaining materials, treatment plants use filtration. Filtration is a physical process. It works by passing water through layers of carefully prepared material. These layers trap particles that are too small to settle by gravity alone. Over time, the filters capture many of the remaining impurities. The most traditional filtration method uses sand filters. These filters are large rectangular basins. Each basin contains several layers of granular material. The top layer is usually fine sand. Beneath the sand may be layers of coarser sand or small gravel. At the bottom are drainage pipes that collect the filtered water. Water enters the filter slowly from above. It spreads across the surface of the sand bed. Then it begins to move downward through the sand grains. As the water passes through the tiny spaces between the grains, particles become trapped. Some particles are caught simply because they are too large to pass through the narrow spaces. Others attach to the surfaces of the sand grains. Over time, a thin layer of trapped material forms near the top of the filter. This layer helps capture even smaller particles. Filtration works slowly and steadily. Water moves downward at a controlled speed. Engineers calculate the correct filtration rate for each plant. If water moves too quickly, particles may pass through the filter. If it moves too slowly, the plant cannot produce enough water for the city. Some treatment plants use slow sand filtration. In this method, water flows through the sand very slowly, often only a few centimeters per hour. A biological layer gradually forms on the surface of the sand. This layer contains harmless microorganisms that consume organic material and certain pathogens. The biological layer becomes part of the filtration process. Other plants use rapid sand filters. These filters move water faster than slow sand systems. Because of the higher speed, the filters require periodic cleaning. Cleaning is done through a process called backwashing. During backwashing, the flow of water is reversed. Clean water is pushed upward through the filter from below. This lifts and loosens the sand bed. The trapped particles are released and washed away. The dirty water is then removed from the system. After backwashing, the filter returns to normal operation. Filtration systems may also include activated carbon. Activated carbon is a form of charcoal that has been processed to create millions of microscopic pores. These pores create a very large surface area. As water passes through the carbon, certain dissolved chemicals attach to its surface. This process is called adsorption. Activated carbon can remove substances that affect taste and odor. It may also capture some organic compounds that remain after earlier treatment steps. Because of this, many plants include carbon filtration in their systems. In some modern facilities, advanced membrane filtration is used. Membrane filters are thin materials with extremely small pores. Water is pushed through these membranes under pressure. The pores allow water molecules to pass through, but they block larger particles and many microorganisms. Different types of membranes exist. Microfiltration removes suspended particles and some bacteria. Ultrafiltration can remove smaller organisms and many viruses. Some specialized membranes can even remove dissolved salts. Membrane systems require careful maintenance. The tiny pores can become clogged over time. Regular cleaning cycles help restore their performance. Sensors monitor pressure changes to detect when cleaning is needed. Regardless of the filtration method used, the goal remains the same. Capture the remaining particles that earlier steps could not remove. Gradually improve the clarity and purity of the water. Prepare it for the final stage of treatment. Treatment plant operators measure water quality continuously during filtration. Turbidity sensors check how clear the water has become. Very low turbidity indicates successful particle removal. Samples may also be tested for microbial presence. By the time water leaves the filtration stage, it is usually very clear. Most particles have been removed. Many microorganisms have been captured or reduced. But a final step is still required. Even extremely clear water can still contain invisible pathogens. Certain bacteria, viruses, or parasites may remain in small numbers. These must be neutralized before the water can safely enter the distribution system. This final protection is provided through disinfection, a process that ensures the water remains safe as it travels through pipes toward homes and buildings. After filtration, the water is very clear. Most particles have been removed. Sediment is gone. Organic fragments have been reduced. Is less than #0. 5# is greater than. Many microorganisms have already been captured by filters. But the water is not yet ready to enter homes. A final step is still required. This step focuses on safety. Specifically, the safety of the water as it travels through the distribution system. That final step is disinfection. Disinfection is the process of neutralizing harmful microorganisms. These microorganisms may include bacteria, viruses, and certain microscopic parasites. Even when their numbers are small, they can cause disease if left untreated. Disinfection ensures that drinking water remains safe for the public. It protects people from waterborne illnesses. It also ensures that the water stays protected while traveling through miles of pipes. One of the most common disinfectants used in water treatment is chlorine. Chlorine has been used for more than a century in public water systems. It is effective at killing many harmful microorganisms, and it continues working as the water moves through the distribution network. This continuing effect is called residual protection. When chlorine is added to water, it dissolves and forms reactive chemical compounds. These compounds damage the cell structures of microorganisms. They disrupt essential biological functions. Over time, the microorganisms become inactive or die. This process happens quietly within the water itself. The amount of chlorine added must be carefully controlled. Too little chlorine may not eliminate all harmful organisms. Too much chlorine can create an unpleasant taste or odor. Treatment plants monitor chlorine levels constantly. Sensors measure the concentration as water moves through the system. Operators also ensure that a small residual amount remains in the water. This residual chlorine continues protecting the water after it leaves the treatment plant. If bacteria enter the distribution pipes later, the chlorine helps neutralize them. Some water systems use a related disinfectant called chloramine. Chloramine forms when chlorine combines with ammonia. It is slightly less reactive than chlorine alone, but it remains stable for longer periods in the distribution system. This longer stability can help maintain consistent disinfection throughout large cities. Many water utilities choose chloramine when pipelines extend long distances. Another method of disinfection uses ozone. Ozone is a highly reactive form of oxygen. It is created by passing oxygen through strong electrical fields. The resulting gas dissolves in water and reacts quickly with microorganisms. Ozone is a powerful disinfectant. It can destroy bacteria and viruses very effectively. It can also break down certain organic contaminants. However, ozone does not remain in the water for long periods. Because of this, some systems still add a small amount of chlorine afterward to maintain residual protection. A third disinfection method uses ultraviolet light. Ultraviolet light is a type of high-energy radiation. When microorganisms are exposed to this light, their genetic material becomes damaged. This damage prevents them from reproducing. Without the ability to reproduce, the microorganisms cannot cause infection. Ultraviolet treatment takes place in closed chambers. Water flows through pipes that contain powerful UV lamps. As the water passes by the lamps, the light penetrates the microorganisms. The exposure lasts only a few seconds, but it is enough to inactivate many pathogens. Like ozone, ultraviolet treatment leaves no lasting disinfectant in the water. For this reason, many plants still add a small amount of chlorine afterward. This ensures protection continues within the pipe network. The choice of disinfection method depends on many factors. Water chemistry, source water quality, size of the distribution system. Each treatment plant is designed to meet the needs of its community. In addition to killing microorganisms, treatment plants must also monitor chemical balance. Water that is too acidic or too alkaline can damage pipes. It may cause corrosion in metal plumbing systems. Engineers adjust the pH of the water to maintain stability. Small amounts of minerals may also be added during this stage. These minerals help protect pipes from corrosion. They form thin protective layers inside the distribution pipes. This prevents metals from dissolving into the water. Some communities also add fluoride during treatment. Fluoride is a mineral that can strengthen tooth enamel. When present in small, controlled amounts, it helps reduce tooth decay. The practice varies depending on local policies and regulations. Throughout the disinfection stage, water quality is monitored continuously. Samples are tested in laboratories. Sensors provide real-time measurements. Operators verify that safety standards are met at every step. Public water systems are among the most carefully regulated utilities in modern cities. By the time the water completes the disinfection process, it is ready for distribution. It is clear. It is microbiologically safe. And its chemical balance has been carefully adjusted. But the journey is not yet complete. The water must still travel from the treatment plant to homes, schools, offices, and hospitals. To do this, it enters another vast network. A network of large pipelines, pumping stations, storage tanks, and underground mains that spread throughout the city. And it is through this quiet network of underground water highways that the treated water begins its final journey toward the tap. After disinfection, the water is considered safe to drink. It is clear. It is chemically balanced, and harmful microorganisms have been neutralized. But the water is still inside the treatment facility. It has not yet reached the city. The final part of its journey is about movement, quiet movement through a hidden network. This network is called the water distribution system. It is a vast system of pipes, pumps, valves, and storage tanks. Most of it lies underground, hidden beneath streets and sidewalks. In many cities, these pipes extend for hundreds or even thousands of kilometers. The purpose of the distribution system is simple. Deliver treated water to every building that needs it. Homes, schools, hospitals, restaurants, offices, all connected through the same quiet network. Water usually leaves the treatment plant through large transmission mains. These are some of the largest pipes in the system. Their diameter can be several meters wide. They carry large volumes of water toward different parts of the city. The flow of water through these pipes depends on pressure. Pressure pushes the water forward. It allows the water to travel long distances. It also helps the water rise into taller buildings. Pressure can be created in two main ways: through pumping and through gravity. Pumping stations use large electric pumps. These pumps push water through pipelines with controlled force. The pumps operate continuously or in scheduled cycles. Their job is to maintain stable pressure throughout the network. Some cities rely heavily on gravity instead. In these systems, water is stored in elevated reservoirs or water towers. Because the water is stored at a higher elevation, gravity naturally pulls it downward through the pipes. This downward pull creates pressure. Water towers are common in many towns and cities. They are tall structures that hold large tanks of treated water. The height of the tower determines the pressure of the water system. The higher the tank sits above the ground, the greater the pressure pushing water through the pipes. Water towers also serve another purpose. They store extra water for times of high demand. For example, during the morning hours when many people shower or cook breakfast, or during the evening when water use increases again. When demand rises, water flows out of the tower into the system. When demand is lower, pumps refill the tower. This quiet cycle helps stabilize the entire network. As water travels through the distribution system, the large transmission mains begin to branch into smaller pipes. These smaller pipes are called distribution mains. They run beneath neighborhood streets, and they carry water closer to homes and buildings. The layout of these pipes often forms a grid. A grid allows water to flow from multiple directions. If one pipe needs maintenance, water can still reach the area through another route. This improves reliability and resilience. Valves are placed throughout the network. These valves allow engineers to control sections of the system. They can reduce pressure in certain areas, or temporarily shut off water to perform repairs. Fire hydrants are also connected to the distribution mains. Fire hydrants provide quick access to water during emergencies. Firefighters connect hoses directly to these hydrants. The pressure within the distribution system allows water to flow out rapidly when needed. Pipes in the distribution network are made from durable materials. Historically, many were made from cast iron. Some older systems still use these pipes today. Modern systems may use ductile iron, steel, concrete, or specialized plastics. Each material has advantages. Strength, resistance to corrosion, flexibility during ground movement. Engineers choose materials based on the needs of the environment and the age of the infrastructure. Water utilities also monitor the distribution system carefully. Sensors measure pressure throughout the network. Flow meters track how much water moves through certain pipelines. If pressure suddenly drops, it may indicate a leak or pipe break. Maintenance crews inspect the system regularly. They repair damaged pipes, replace aging infrastructure, and flush sections of the network to maintain water quality. Even though the water has been disinfected, it must still remain protected as it travels through the pipes. That is why a small disinfectant residual remains in the water. This residual continues guarding against microbial growth. The journey through the distribution system can take hours. In some cases, it may take a day or more for water to move from the treatment plant to distant neighborhoods. The exact travel time depends on distance, demand, and system design. Eventually, the water reaches the smallest pipes in the system. These pipes are called service lines. A service line connects the main distribution pipe to a specific building. Every home and building has its own service connection. From this point, the water leaves the public network. It enters the private plumbing system of the building. Pipes inside the walls and floors guide the water toward sinks, showers, washing machines, and drinking fountains. The long journey that began in rivers, lakes, or underground aquifers is now nearly complete. The water has traveled through collection systems, treatment processes, filtration beds, disinfection chambers, and finally, through miles of quiet underground pipes. Now it arrives at the final point of delivery, the simple faucet inside a home. And it is there, at the moment the tap begins to turn, that the hidden infrastructure of the entire water system reveals its final step. At the end of the distribution network, the water arrives at a building. It reaches the service line that connects the public system to a private structure. This structure may be a house, an apartment building, a school, or an office tower. From this point forward, the water moves through the building's plumbing system. The service line is a small pipe that branches off from the main distribution pipe under the street. It runs underground toward the building. This pipe carries water under steady pressure from the city system. When the service line reaches the property, it usually passes through a shutoff valve. This valve allows the water supply to be turned off if repairs are needed. Just inside the building, the water often flows through a water meter. The water meter measures how much water the building uses. Utilities use this measurement to calculate billing. The meter works by detecting the flow of water through the pipe. As water moves through the meter, internal components rotate or sense the flow electronically. Modern meters may send readings automatically to the water utility. This allows accurate monitoring without manual inspection. It also helps detect unusual spikes in water usage that might indicate leaks. After passing through the meter, the water enters the building's main supply pipe. This pipe distributes water to different parts of the structure. In small homes, the system may be relatively simple. In large buildings, the plumbing network can become quite complex. Pipes branch outward through walls, floors, and ceilings. These branches carry water to kitchens, bathrooms, laundry areas, and mechanical systems. Each fixture receives water through its own connection. The plumbing system usually contains two separate lines, one for cold water, one for heated water. Cold water arrives directly from the service line. Heated water is produced by a water heater within the building. Water heaters warm the water to comfortable temperatures for bathing and cleaning. Some heaters use electricity. Others use natural gas. Inside the heater, a tank stores water and gradually raises its temperature. In tankless systems, water is heated instantly as it flows through heating elements. Once heated, the warm water flows through separate pipes toward showers, sinks, and appliances. The cold and hot water lines meet again at mixing valves inside fixtures. These valves allow users to adjust the temperature by blending the two flows. Pressure from the city system continues pushing water through the building's pipes. In taller buildings, additional pumps may be installed. These pumps help lift water to upper floors. Some high-rise buildings also use rooftop storage tanks to maintain pressure. Inside the plumbing system, pipes are carefully arranged to prevent contamination. Backflow prevention devices are often installed. These devices stop water from reversing direction in the pipes. Without them, contaminated water from appliances or industrial systems could flow back into the drinking supply. Plumbing codes require specific materials for pipes. Copper pipes are common in many homes. Plastic materials such as PEX or PVC are also widely used. These materials resist corrosion and allow safe transport of drinking water. As water moves through the plumbing system, it remains under pressure. That pressure allows it to reach the final point of use. A faucet, a shower head, or a drinking fountain. A faucet is a simple mechanical device. Inside the faucet is a valve that controls the flow of water. When the handle turns, the valve opens. Pressurized water moves through the opening and flows out of the spout. The flow continues as long as the valve remains open. When the handle turns back, the valve closes. The water stops flowing. The pressure remains inside the pipes, ready for the next use. At this moment, the long journey of the water becomes visible. Clear water flows into a sink, into a glass, or into a cooking pot. What appears simple at the surface is the result of a vast system working quietly in the background. The water may have traveled from a distant river or from a deep underground aquifer. It passed through treatment plants, filtration beds, disinfection chambers, then through kilometers of underground pipes before reaching this faucet. Every drop that arrives has followed this careful process. Collection, treatment, distribution, delivery. A quiet chain of systems that operate continuously, day and night. Most of the time, people do not think about this infrastructure. The water simply appears when the tap is turned. Clear, clean, ready to drink. Yet behind this everyday moment lies one of the most carefully engineered systems in modern society. A system designed to protect public health, to support cities, and to deliver one of the most essential resources for life. And once the water has been used inside the home, its journey is not completely finished, because it will soon begin another quiet path through an entirely different system beneath the city. Once the water has been used inside the home, it begins another quiet journey. This journey moves in the opposite direction. not toward homes, but away from them. Used water must be carried away safely. It cannot remain inside buildings, and it cannot simply flow across the ground. Instead, it enters another hidden network beneath the city. This network is called the sewer system. Its purpose is to collect wastewater and transport it to treatment facilities. Wastewater includes water from sinks, showers, toilets, washing machines, dishwashers. All of these flows eventually leave the building through drainage pipes. Inside the home, drainage pipes operate differently from supply pipes. Supply pipes rely on pressure. Drainage pipes rely on gravity. The pipes are angled slightly downward. This slope allows wastewater to flow naturally toward the sewer line. Each sink, shower, or appliance connects to the drainage system through a pipe. Beneath many fixtures sits a curved section of pipe called a trap, often shaped like the letter U or P. The trap holds a small amount of water inside the bend. This water forms a seal. The seal prevents sewer gases from traveling back up into the building. Above the drainage pipes, another set of pipes rises upward through the walls. These are called vent pipes. Vent pipes allow air to enter the plumbing system. This airflow keeps pressure balanced inside the pipes. Without vents, drainage could become slow or unstable. As wastewater leaves individual fixtures, it joins larger drainage pipes inside the building. These pipes combine flows from multiple rooms. Eventually, they connect to the building's main sewer pipe. The main sewer pipe exits the building underground. Outside the building, the pipe connects to a municipal sewer line beneath the street. From here, wastewater begins traveling through the public sewer network. The sewer network resembles the water distribution system in some ways. It also consists of underground pipes extending throughout the city, but its direction of flow is reversed. Instead of delivering water outward, it collects wastewater inward, is less than Hashone. 0 hash is greater than toward centralized treatment facilities. Sewer pipes are usually larger than household drainage pipes. They must carry the combined wastewater from many buildings. Entire neighborhoods may drain into a single main sewer line. Like household pipes, most sewer lines rely on gravity. The pipes are built with a gentle downward slope. This slope guides the wastewater gradually toward lower elevations. Over time, the flow moves toward larger interceptor sewers. Interceptor sewers are very large underground pipelines. They collect wastewater from multiple smaller sewer lines. These interceptors carry the combined flow toward wastewater treatment plants. In some areas, gravity alone is not enough to move the wastewater. The terrain may be flat, or the treatment plant may lie at a higher elevation. In these cases, pump stations assist the flow. A sewer pump station collects wastewater in a chamber called a wet well. When the level rises high enough, pumps activate automatically. The pumps lift the wastewater into a higher pipeline. From there, gravity flow can continue again. Sewer systems must also handle rainwater in some cities. Older urban areas sometimes use combined sewer systems. In these systems, stormwater and wastewater share the same pipes. During heavy rainfall, large volumes of water enter the sewer network. This can increase the flow dramatically. Modern systems often separate these flows. Stormwater drains carry rainwater directly to rivers or retention basins. Sanitary sewers carry only wastewater from buildings. Separation reduces the burden on treatment plants. Along the sewer network, maintenance structures called manholes appear at intervals. Manholes allow workers to access the underground pipes. They provide entry points for inspection, cleaning, and repairs. From the street surface, they appear as circular metal covers. Sewer systems must be carefully maintained. Debris can accumulate inside the pipes. Grease from kitchens may harden along pipe walls. Tree roots may grow into small cracks. Maintenance crews regularly inspect and clean the network. Specialized equipment flushes pipes with high-pressure water. Cameras may be sent through the pipes to identify damage. Early detection helps prevent larger failures. Over time, the wastewater from thousands of homes gathers within the sewer system. The flow grows larger as pipes merge together. Small neighborhood drains become city-wide channels of wastewater movement. Eventually, the combined flow reaches the entrance of a wastewater treatment facility. This facility performs another set of processes designed to remove contaminants from the used water. The goal is to protect rivers, lakes, and oceans from pollution. At the treatment plant, wastewater will pass through screening systems. Settling tanks is less than #0. 5# is greater than biological treatment processes. And additional purification stages. Only after this careful treatment can the water safely return to the environment. The quiet cycle continues. Water leaves the environment, travels through cities, serves homes and communities, and eventually returns to nature once again. And it is inside these wastewater treatment facilities that the used water begins its final process of cleaning before rejoining the natural water cycle. Wastewater eventually arrives at the treatment facility. By the time it reaches this point, it has traveled through many underground pipes. It has collected water from homes, from sinks and showers, from washing machines and toilets. All of this used water now gathers in one place. The purpose of the wastewater treatment plant is simple. Remove contaminants from the water, protect the environment, and return the cleaned water safely back to nature. The process begins as the wastewater enters the plant through large pipes. The water is cloudy. It contains particles of many sizes. Some float, some sink. Some are dissolved in the water itself, The first stage is called preliminary treatment. This stage removes large objects that could damage equipment. Wastewater passes through metal screens. The screens catch items such as paper, plastics, and other debris. These materials are collected and removed from the system. After screening, the water enters a chamber where heavy particles settle out. Sand, small stones, and other dense materials sink to the bottom. This step is called grit removal. Removing grit protects pumps and pipes from abrasion. Once large debris and grit are removed, the water moves into primary treatment tanks. These tanks are large and quiet. The water flows slowly through them. Gravity begins working again. Heavy organic particles sink to the bottom. Grease and oils rise toward the surface. Mechanical scrapers move slowly across the tanks. They collect the settled material from the bottom. This material is called primary sludge. Floating grease and oils are skimmed from the surface. Primary treatment removes a significant portion of solid waste. But much of the contamination remains dissolved or suspended in the water. For this reason, the water continues to a second stage. This stage is called secondary treatment. Secondary treatment focuses on biological processes. It uses naturally occurring microorganisms. These microorganisms consume organic material present in the wastewater. The water enters large aeration tanks. Air is pumped into the tanks through diffusers. This air supplies oxygen to the microorganisms. With oxygen and nutrients, the microorganisms grow and multiply. As they feed, they break down organic waste. Substances that once polluted the water are gradually converted into simpler compounds. Much of the organic matter becomes part of the microbial biomass. This mixture of water and microorganisms is called activated sludge. The name reflects the active biological processes taking place within the tank. After sufficient time in the aeration tanks, the mixture flows into secondary settling basins. These basins allow the biological solids to settle out of the water. The microorganisms gather at the bottom of the tank as sludge. Some of this sludge is returned to the aeration tanks to maintain the microbial population. The rest is removed for further treatment. At this stage, the water has become much clearer. Most organic pollutants have been removed. Suspended solids have largely settled out. Yet a final stage is often applied to ensure the highest level of environmental protection. This stage is called tertiary treatment or advanced treatment. Different plants use different methods at this stage. Some systems filter the water through sand or specialized membranes. Others remove nutrients such as nitrogen and phosphorus. These nutrients can cause excessive algae growth in rivers and lakes if left untreated. Chemical or biological processes may be used to capture these nutrients. The goal is to leave the water as clean as possible before it returns to the environment. In many facilities, the final step is disinfection. Even after treatment, small numbers of microorganisms may remain. Disinfection reduces these organisms to safe levels. Chlorine, ultraviolet light, or ozone may be used for this purpose. After disinfection, the water is ready to leave the treatment plant. It flows out through a structure known as the outfall. From here, the treated water enters a river, lake, or coastal area. In some regions, treated water may also be reused for irrigation or industrial purposes. The solids collected during treatment follow a separate path. Sludge from the settling tanks is thickened and stabilized. It may be treated through digestion processes that reduce pathogens and odors. In some cases, the treated biosolids are used as soil amendments in agriculture. The wastewater treatment plant quietly completes an essential task. It protects natural ecosystems. It prevents pollution from entering rivers and oceans. And it helps close the loop of the urban water cycle. Water that once flowed through homes has now been cleaned again. It returns to the environment where it may evaporate, fall again as rain, or flow back into rivers and aquifers. Over time, that same water may once again begin the long journey toward a treatment plant, a distribution pipe, and eventually a household tap. The cycle continues quietly, often unnoticed, yet essential for the functioning of every modern city. And with this final step in the water's long journey completed, it becomes possible to step back and quietly reflect on the hidden infrastructure that makes this everyday convenience possible.